Hello everybody, and welcome to our video on geometric sequences and series. So we've talked about general sequences and series. Then we talked about the specific type of arithmetic sequences. So now we're just talking about one more specific type of sequences that's pretty common in applications, and that's of geometric sequences. So definition: the sequence A1, A2, A3 through AN ... is a geometric sequence, or in other words, a geometric progression, if there is a number R such that each term except the first in the sequence is obtained by multiplying the previous term by R. So one thing to add in here is that, keep in mind that essentially these sequences act as lists, which is, of course, why we sometimes use this term geometric progression. All right, but when we're writing out this list, what this is saying is that you get each term in our list by multiplying the previous term by R. That number R is called the common ratio of the geometric sequence. Why is that? Well, notice this definition of a geometric sequence is recursive. It tells us that if I have a term a sub n plus 1, I found that term by taking the previous term a sub n and multiplying by R. So if I divide by a sub n, I get a sub n plus 1 over a sub n equals R. So any term divided by the term previous should give me the same number R. So let's take a look at this example. Determine whether each sequence is geometric. If it is, then find the first term and the common ratio. So for A here, well, let's take A2 divided by A1. That's 4 divided by 2. That's 2. Done. All right, that's the first one. So A3 divided by A2, what do we get there? It's 8 divided by 4. That's 2. So far, so good. They're matching up. A4 over A3. That's 16 divided by 8. That's 2. Hey, I got the same thing for all three of these. So yes, it is geometric. Our first term is just the 2. And our common ratio R is also 2, coincidentally. It, of course, doesn't have to be the same. All right, now let's go ahead and take a look at B here. If I take A2 divided by A1 for question B, that's 1 divided by 1, which is 1. Okay, so far so good. What about A3 divided by A2? That's 3 divided by 1. That's 3. These are not equal. Okay, so that did not match our previous ratio. So this is not geometric. So very similar to these types of problems with arithmetic, it's just we're looking for common ratios rather than common differences. All right, now the general term of a geometric sequence. So every geometric sequence can be written in the form A1 times R, A1 times R squared, ... A1 times R to the n minus 1, where R is the common ratio. Notice the nth term of the geometric sequence is a sub n equals a1 times r to the n minus 1. So in case it's not clear here, let's just think about what this is saying. My first term is given, and my second term is what I get from taking a1 and multiplying it by r. And my third term is what I get from taking a2 and multiplying it by r, but that's a1 times r times r. So that's a1 times r squared. So notice, whatever our value for n is, the power of r is 1 less than that, right? This is to the first power. And you could think of this, the first term, as being a1 times r to the 0 power, because r to the 0 power is 1. So in other words, our general formula here is always just going to be a sub n equals a1 times r to the n minus 1. Okay, so let's go ahead and move on to an example here. Find a1r and a sub n for the given geometric sequence. So you're told explicitly that this is geometric, so you don't need to check that. But we should find what r is, or a1 is, that's -3. Okay, so now what's r? Well, we can take a2 divided by a1, that's going to be equal to r. It's -6 divided by -3, that's 2. And so now if I plug into my formula, a1 times r to the n minus 1, what do we get? We get -3 times 2 to the n minus 1 power. Okay, now find n for the given value of a sub n in the geometric sequence. So a sub n is 1 over 2187. And now this is a little tricky because we've got something alternating. We've got 3, -1, 1/3, so forth and so on. So a1 is just 3. All right, well now what do we get when we take a2 divided by a1? It's -1 over 3. Okay, so that means my value for r is -1/3. So my general formula should look like 3 times, not plus. Brain went back to arithmetic for a second. 3 times -1/3 to the n minus 1 power. Now, this could be a little bit tricky to solve as is. So what I'm going to do is rewrite this expression a bit, because what I need to do is set it equal to 1 over 2187 and solve from there. So the first thing I'm going to do is rewrite this as 3 times -1 to the n minus 1 over 3 to the n minus 1 power. So my exponent laws tell me I can write this as -1 to the n minus 1 over 3 to the n minus 2 power, right? I take this n minus 1, subtract 1, combine it all like that. Now, that becomes a little weird. So let's see what happens here. So this is often something that I think students find a little tricky, but it's not as hard as it seems. We get -1 to the n minus 1 over 3 to the n minus 2. So I need to know that -1 to the n minus 1 is going to be equal to 1 here. But I can't actually solve that, right? I don't really have any good algebraic approach to dealing with this negative alternating term going back and forth here. So what we're going to do is basically, for now, ignore the -1 to the n minus 1. And then we'll just check that our answer makes sense afterwards. So, in other words, for these two things to be equal, if I ignore this part, I just need these denominators to be equal. So that implies 2187 should be equal to 3 to the n minus 2 power. And so there's a number of ways I could approach this, but I think the easiest one is to just figure out how to rewrite 2187 as a power of 3. Now that might seem tricky, but if you just multiply 3 out over and over in a calculator, just see how many times it takes to get to that number. So I did it in my calculator. I get 3 times 3 times 3 times 3 times 3 times 3 times 3. In other words, 3 to the 7th power equals 3 to the n minus 2. Now you might not get an exact answer here, in which case you would take log base 3 of both things and solve for n, and then you would just use a calculator to give a decimal approximation. But in this case, I know that I have to get an integer answer because sequences only deal with integer values of n. So it doesn't really make sense to expect any other answer. Now, if 3 to the 7 equals 3 to the n minus 2, obviously that can only happen if their exponents are the same. So 7 has to equal n minus 2, so n has to equal 9. So now we're going to go back and check a sub 9 equal to negative 1 to the 9 minus 1 power over 3 to the 9 minus 2. And all I'm checking here really is to make sure that I get that positive 1 up top that I expected to get for this value. So negative 1 to the 8th power is 1, so that's 1 over 3 to the 7th. That's 1 over 2,187. So again, I know that this alternating term sends these terms back and forth between negative 1 and 1. I don't really have a good way algebraically to deal with that while dealing with this denominator at the same time. So we just ignore it, solve for an n value that works to give us the denominator we wanted, and just check and make sure that when we plug that in, we actually still get the correct answer, as opposed to like getting a negative 1 up top. Okay, so that's it. N equals 9. So now let's take a look at the sum of the terms of a finite geometric sequence. So let a1, a2 through an be the first n terms of a geometric sequence with the first term a1 and common ratio r. The sum s sub n of these terms is s sub n equals the sum from I equals 1 to n of a1 times r to the I minus 1, which is equal to a1 times 1 minus r to the n, all divided by 1 minus r. And of course, this only works if r is not equal to 1 because we can't divide by 0. So this proof uses a similar kind of clever trick to the proof for that arithmetic sum formula we did, the 1 plus 2 plus 3, but it's a little bit different. So here, I write out my sum long ways. So the sum s sub n of the first n terms, that's a1 plus the second term is a1r plus the third term, a1r squared, plus dot dot dot, and this is the nth term. Remember, a1 times r to the n minus 1 is actually the nth term. Now, if I multiply both sides of this equation by r, then I get r times s sub n equals a1r plus a1r squared plus dot 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 plus a1r to the n minus 1 plus a1 times r to the n. So all we've done is taken this sum we already had and multiplied it by r on both sides of the equation. So now these two things are equal. And so now the clever trick here is to take the first sum minus the second sum. So s sub n minus r times s sub n. And what do we get? Well, if we're subtracting these things, we're going to cancel all the matching terms. And all that's going to be left is a1 minus this last term, a1 times r to the n. So when I factor out s sub n and I factor out a1 on the right side, I get s sub n times r, 1 minus r, I mean. Let me try that again. S sub n times 1 minus r equals a1 times 1 minus r to the n. Divide out the 1 minus r, and finally we get s sub n equals a1 times 1 minus r to the n divided by 1 minus r. So that's how we get our sum formula for the finite terms of a geometric sequence. So let's go ahead and tackle an example here. So here we want to find s sub 10, so the sum of the first 10 terms. So remember, we always want to write out our sum formula. So s sub 10 equals, so what is our sum formula? It's a1 times 1 minus r to the nth, n in this case is 10, over 1 minus r. So that means I already know what 10 is, of course, that's given here explicitly. I need to figure out what r and a1 is. a1 is easy enough, that's just 6. So what's r? Well, we can just take a2 divided by a1. It's 2 divided by 6, that's 1/3. So now we plug this missing information into our sum formula. We get 6 times 1 minus 1/3 to the 10th divided by 1 minus 1/3. Okay, so before we start to do the algebra on this, I just want to talk about like a general principle here for simplifying these problems. Typically, you're going to be asked and expected to provide a simplified answer when you're given any problems like this. One of the best things you can do is whenever you have terms to a power, leave them raised to that power until the very end. Don't start multiplying them out because it'll be much harder to simplify. You'll get fractions that are just huge. And it'll be hard to figure out how to simplify them if you multiply everything out first. So instead, leave everything in terms of the powers for as long as you can. So I'll demonstrate what I mean here. This becomes 6 times 1 minus, and 1/3 to the 10th is 1 over 3 to the 10th power, because 1 to the 10th power is just 1. And 1 minus 1/3 is 2/3. And so when I divide by 2/3, that's the same thing as multiplying by the reciprocal. And notice that 6 over 2 is just 3. So now I could say 3 times 3 is 9, but I'm going to write it as 3 squared. Again, as you'll see in the next step, that's going to help me simplify things first. Okay, so now I'd like to be able to distribute this and simplify it, but it's going to be easier for me to do that if the first thing I do is find a common denominator inside here. So this becomes 1 is 3 to the 10th over 3 to the 10th. I'll break this up into smaller steps here for this first example. Minus 1 over 3 to the 10th. So this is 3 squared times 3 to the 10th minus 1 over 3 to the 10th. So notice that now I have 3 squared over 3 to the 10th. That lets me simplify this to just 3 to the 8th on bottom. Now I can't factor 3 out of both terms on top, which means I can't simplify this any further. So by leaving everything in terms of exponents first, instead of getting huge numbers, which you're going to get, you would get even bigger numbers, and then you would usually struggle to find the common factors to simplify them. But now, since we left everything in terms of powers of 3, we know I can't factor out any more powers of 3 up top because there's no factor of 3 here. So I've simplified this thing as much as it can be. Now I can just go straight to plugging this into a calculator. This gives me 59,048 divided by 6,561. And that is simplified and my final answer. Okay, so let's take a look at this next example here from I equals 1 to 8 of 2 times 3/5 to the I minus 1 power. So it helps if we take a look back at our general formula. When I have this sum form, I equals 1 to n of a1 times r to the I minus 1, that is my standard formula, and it includes the information for a1 and r. So sometimes you're given something that isn't in that standard form, and you might have to manipulate it first, but let's just write out our standard form and see if it matches up. So it does. A1 is 2 here, right? We've got a number. We're starting at I equals 1 for both of these. We've got the same value for n for both of these. So what do we got? N equals 8. We've got A1 is 2. And R is 3/5. The thing to look out for here in particular is this power has to be the same. So sometimes you'll be given something where the expression you're given isn't to the I minus 1 power. And if it's not in that form, then the formula doesn't work. and then you might have to use some exponent laws to rewrite your expression a little bit. But in this case, we're in good shape because we can go ahead and straight up apply our formula. And remember, your formula is a1 times 1 minus r to the nth power over 1 minus r. And so a1 here is 2. This becomes 1 minus 3/5 to the n power. That's 8 divided by 1 minus 3/5. And we have a similar algebraic issue for this problem. So we'll just go through the same process. 2 times 1 minus 3 to the 8ths over 5 to the 8ths. Divided by 1 minus 3/5, that's 5/5, minus 3/5, that's 2/5. Division is multiplication by the reciprocal. So I'll write this as 5 over 2 times 1 minus 3 to the 8th over 5 to the 8th. The 2 over 2 cancels, that's kind of nice. And this becomes 5 times 1 minus 3 to the 8th power over 5 to the 8th power. Now I'm going to find a common denominator here. So this becomes 5 times 5 to the 8ths over 5 to the 8ths minus 3/8 over 5 to the 8ths. Now I can combine that fraction. That becomes 5 times 5 to the 8th minus 3 to the 8th all over. Try to write that a little better. 5 to the 8th power. And so now I see I've got this 5 to the first power over here over 5 to the 8th power. So I can simplify that denominator down to 5 to the 7th. So this gives me 5 to the 8th minus 3 to the 8th over 5 to the 7th. Now notice, I can't factor out a 5 of both of these terms, so I can't simplify anything else with my denominator. That's how I know I'm done and that I've fully simplified this thing. So we just, at this stage, can plug straight into our calculator and know that we're going to get a fully simplified answer. Up top, we get 384,064 divided by 5 to the 7th, which is 78,125. All right, and that's it for that sum. All right, so now we're going to take a look at the sum of the terms of an infinite geometric sequence. So if the absolute value of r is less than 1, the infinite sum a1 plus a1r plus a1r squared plus ... is given by s equals the sum from I equals 1 to infinity of a1 times r to the I minus 1 equals a1 over 1 minus r. So this just comes from our other sum formula, our partial sum formula, a1 times 1 minus r to the n over 1 minus r. So we're asking, remember, this partial sum, the sum is just the limit. What happens when n goes to infinity of our partial sum? So when we're looking at this geometric sequence here, this geometric sum, when I take the partial sum, this is the only part that's impacted by n. And if the value of r is less than 1, this thing goes to 0. So to think about that, like as an example, if I take 1/2 to the nth power, right? 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 to the third power is 1/8, so forth and so on, right? So the higher you raise the power of r to the n, the smaller the value you get, and it gets closer and closer to 0. So if this term approaches 0 for this partial sum, then what do you get left with? You get left with a1 times 1 over 1 minus r, which is exactly what our formula is here. Okay, so now we're given this general formula 1/2 plus 1/4 plus 1/8 plus 1/16. So the first thing to figure out is this geometric? Well, if I take 1/4 divided by 1/2, that's 2 over 4, right? Multiplied by the reciprocal, that's 1/2. So that's my a2 over a1. What's my a3 over a2? It's 1/8 over 1/4. That is also 1/2. And a4 over a3. That's 1/16 over 1/8. That's also 1/2. So yeah, it's geometric. So that tells me I can apply the geometric formula here. So S equals A1 over 1 minus R. And A1 is just the 1/2. 1 minus R. R is 1/2. That's my common ratio, right? So this is 1/2 divided by 1/2, which is 1. So notice this is the same example that we did at the end of our first video on sequences and series. And in that video, we were just talking about, how to think of this sum, 1/2 plus 1/4 plus 1/8 plus 1/16, in terms of the number line, right? And what values it's approaching. But now we see that that example was actually a specific geometric sequence, a geometric sum, I should say, and that we can use these tools for infinite geometric sequences to solve that same problem. Okay, so now let's take a look at another problem that's a little more complicated, but it involves a geometric sum. So, well, first, let me kind of go back to this previous problem. I'm going to use this to expand on an idea that's relevant to the next problem. So what I want to illustrate here is that when we're talking about these infinite sums, someone might say, well, time can't last forever, so you can't really ever take an infinite sum, so why are we doing this? Well, we're doing it because even though in terms of real-world applications, you're going to be dealing with things that are finite, the values can be so large for the number of terms in your sum that the difference is meaningless. So what do I mean there? Let's just take a look at the sum of the first 10 of these terms. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256 plus 1 over 512 plus 1 over 1028. Now, spoiler alert, I know what this adds up to. It adds up to 1027 divided by 1028. I wrote 88 for some reason. That should be 28. So let's plug this into a calculator. This is approximately 0.999. Basically, that's it, right? There's a 0 after that. 0.999,027, so forth and so on. So that's less than 1/1000th of a difference between this answer and 1. So the point being that whenever you're dealing with applications where the number of repetitions is extreme and computing the number of actual repetitions would be way too cumbersome, you can often, if you know that this thing is like geometric in this case, or convergent in general, you can often use this infinite form of the sum to actually approximate the real finite form, and you will get answers that are so close that for practical applications, it's perfect. It's exactly what you need. And notice, this was just 10 terms. Imagine how accurate this would have been if I was doing something that was adding 100 terms together or 1,000 terms together. The accuracy would be even better by orders of magnitude. So with that being said, let's move to this next problem. A particular bouncy ball always rebounds 3/4 of the distance, 3/5 of the distance that it falls. If the ball drops from a height of 9 meters, how far will it travel before it stops? So what we're going to do here is assume that this ball actually bounces forever. It doesn't. Eventually, at some point, the forces of friction and gravity overtake this thing and it stops moving. But we're going to model this behavior as if it bounced this 3/5 the distance it falls infinitely many times. And that's okay, because what we know is I don't even need to know the actual number of times the ball will bounce. I have no clue. Maybe this ball will bounce 1,000 times before it stops. Maybe it'll only bounce 100, maybe 50. But I do know that it's going to bounce enough times that I can use an infinite sum to approximate the finite sum that it actually represents. So that's really the heart of the issue here. So let's go ahead and draw a picture and see if we can kind of make this thing a little solvable here. So we imagine this ball, it drops and it falls 9 meters. And then when it bounces back up, it bounces back up 3/5 of that 9 meters. So I've multiplied my 9 meters by 3/5. Now what goes up must come down. So it's got to fall 9 times 3/5 again. But when it bounces, when it hits the ground, it bounces back up another 3/5 times that. Okay, well, that's really just 9 times 3/5 squared. And then it's going to fall down 9 times 3/5 squared. And then it's going to bounce 9 times, well, it's going to bounce 9 times 3/5 cubed, right? Because we're multiplying by 3/5 again. And it's going to fall 9 times 3/5 cubed. Okay, I think we see the pattern now. But one of these things is not like the others. See, all of these, except for the first, are paired up with a fall that's the same exact distance as the bounce. And we're talking about total distance traveled. So we're treating up and down as the same, right, as both positive. So this is really 2 times 9 times 3/5. And this is really 2 times 9 times 3/5 squared. And 2 times 9 times 3/5 cubed. So we have a problem. How can I make one formula to deal with this case when I have this outlier term that kind of messes it up? Well, what I'm going to do is just add a fake term here. And imagine that it had already bounced up 9. Now I'm going to have to compensate for that later, but that's okay, right? I'll just think of this as 2 times 9 plus so forth and so on. So let's figure out how to write our sum. So our sum that we're dealing with here is the infinite sum, where the first term is 2 times 9, that's 18, times 3/5 to the I minus, I should say n minus 1 power, because I'm using n as my subscript. So this is my sum, and when I apply my sum formula, I get a1, that's 18, divided by 1 minus r. That's 18 over 2/5. That's 18 times 5 halves. 18 divided by 2 is 9. 9 times 5 is 45. But this is not the answer, because we have an extra 9 meters in here. So the actual distance traveled is the 45 meters minus the 9 that we added in extra. So the actual distance is 36 meters. So just keep in mind, all we did here was added this extra one at the beginning so that we had a nice formula here that matched up for all of our terms, right? Since each of these others was doubled, we just added this to double the first one. And then once we found that sum, we said, well, the actual distance, that had included an extra 9 meters, so we subtract that to get the actual distance. And that's it. So again, if you took a look at a bouncy ball like this, if you started writing out these terms and you just wrote out 10 of these sums, you'd see very quickly that this is a super, super good approximation of how far that bouncy ball is going to actually travel before it comes to a stop, even if it was only to bounce 10 times. Okay, so hopefully that makes sense and you can see why these ideas are very valuable in applications. And that's going to be it for this video. Thanks for watching.